of the reduced Lagrangian in CPN is non-zero, then L is not going to be Z2 displaceable. And by the way, SC is me, it's not Salam Connolly. She's the next speaker. The strategy of the proof is going to be as follows. We're going to construct a Z2 equivariant quantum cohomology, QH of L, that satisfies the property you would expect, which is if L is equivalently displaceable, then the equivariant quantum cohomology vanishes. Then we're going to compute it in the case we have, and we're going to see that it's just a direct sum of the quantum cohomology downstairs plus a shift, and then we win, essentially. There are two main inspirations for this paper. The construction of the equivariant quantum cohomology is an open string analog of work by Seidel and Seidel-Smith. However, they work over a power series ring in one variable, and we work over a polynomial ring in one variable. And we will see this subtle difference is very important, but the construction follows that vein. And the second is to actually compute it. We're going to use arguments present in a paper by Biran-Khanevsky on their Floer-Gisin sequence, and in particular, their so-called Floer-Euler class will make an appearance in the computation. So we will actually see it appear. First, a quick reminder on quantum cohomology. So we start with a monotone Lagrangian L with minimal Maslov number 2. I equip it with a Morse function and a pseudo-gradient V, and I pick a generic, almost complex structure. Then the chain complex is just going to be the free span over lambda, where lambda is just Laurent series in one quantum variable Q, and spanned by the zeros of the pseudo-gradient, or the zeros of F. And the differential is given by counting Pauli trajectories and weighing them, where the Q term is going to be weighed by the Maslov index. So what is a Pauli trajectory? Essentially, I'm just going to show a picture. It's a configuration like this. So this is a Pauli trajectory from X to Y, and not from Y to X, because we're doing cohomology, but that's not so important. So I flow via the gradient flow. Then eventually I can choose to have a holomorphic disk, and then there's another, like it lands in some point, and then I can follow the gradient for a finite amount of time, and then I do so again, and then I just flow until I reach the other critical point. And the rigid count of this is going to be a finite count. So to define Z2 equivariant cohomology, first I'm going to set the scene with the coefficients. So we will work again over K equals Z2 and the ring of Laurent series, but we'll also add polynomials K adjoint E, where E is a degree 1 variable. So this is the main difference with Seidel and Smith's work. We're working with just K of E and not power series in E. The generators are going to be given essentially the same. So we pick an ordinary like Morse function and pseudo-gradient on L, and we set the equivariant chain complex to be the span by the zeros of V, tensor Laurent series, tensor this time with K adjoint E. Intuitively, we're going to consider perturbation data over the classifying space of Z2. So recall that we have an infinite dimensional smooth manifold S infinity, which is just given by all the infinite tuples of real numbers, such that finitely many are non-zero, such that the norm is equal to 1. And the classifying space is just the quotient of S infinity by the antipodal action. So if I multiply everything by -1, I remain in S infinity. And this is RP infinity. There is a Z2 equivariant pseudo-gradient field on S infinity with respect to the Morse function given here by the sum of the index times xi squared. And the zeros are going to be precisely the poles of S infinity. So a pole, the jth positive pole, so Vj plus, will be the point that has 1 as its jth entry, and the jth negative pole will be the the one that has -1 as its jth entry and zeros everywhere else. Note there is a self-similarity map which just shifts all the coordinates by 1. So I map x0, x1, blah, blah, to just 0, x1, blah, blah, blah. How do we define the equivariant differential? So we start with V and J such that usual quantum homology is defined. And now I consider an S1 family of pseudogradients and almost complex structures, V eta, J eta, such that if I go to minus eta, I just pull back the perturbation data by the involution. And near every positive pole, V eta, J eta doesn't actually depend on eta and is equal to the fixed Vj. So in particular, note that if I go to a negative pole, I will have the involution of V comma J. So I won't have a copy of Vj, I will have a copy of the involution of Vj. So it won't be the same vector field. This is important later. And they are tau invariant. So the self-similarity map preserves this perturbation data. So we're going to define the equivariant differential as a deformation of the usual quantum differential. And it's going to be defined, the kth term is going to be the count of p comma gamma, where gamma is a gradient line of S, joining V0 plus to either Vk plus or Vk minus. And p is a Pearly trajectory above gamma, where the pearls are V eta, G eta holomorphic. I'm going to make a picture, and this is going to be a bit clearer. And in particular, if gamma joins V0 plus to Vk plus, then we just set it to be the weight of the counts by the Maslov index. Note that since V is the same at all the poles, then this Pearly trajectory will land at something in the chain complex that I actually have. It's going to be the same chain complex, so Y is also in the chain complex of V. So here is a picture. So I have gamma downstairs in S infinity. And above it, I have a sort of domain-dependent vector field, a family of vector fields. And I can flow. And eventually, at some point, I may decide to make a holomorphic jump. What holomorphic structure do I use? Well, it's simple. I just look at the holomorphic structure downstairs. So I project to gamma. And I go like, OK, so this point gives me a holomorphic structure. I make a jump, then I flow again, then I may decide to do another jump, etc., etc. And so here I started at yx, at y, and then I ended at x. So this is the case where I go from V0 plus to Vk plus. However, if gamma joins V0 plus to Vk minus, there's a subtlety, because as we said, when I go to a negative pole, I am no longer in the zeros of V. It's not the same chain complex, it's the zeros of the involution of V. So we remedy this simply by twisting. So we just apply the involution, and then I'm going to get a zero of the original vector field. So it's this twist that I'm going to use. So it's the same count, only twist. And finally, I can set dx to be this sum over all case of dx plus and dx minus. I'm writing here the sum to infinity, but by Maslov index considerations and indices, because everything is monotone, actually there are finitely many terms. So we do land in the polynomial ring. We don't get a power series. Okay. So the definition of the cohomology. Well, it turns out that the equivariant differential squares to 0. And surprise, surprise, this follows by looking at the one-dimensional moduli space, and bubbling can't occur. So the only kind of loss of compactness can be breaking. And this gives you the dx squared terms. That is the usual Floer homology argument. The resulting cohomology, which is QHX, satisfies what you would expect, which is it's independent of the choice of all the perturbation data on S infinity that you made and on the original one. If L is equivalently displaceable, then QH star ec of L vanishes. So that's one of the conditions we wanted. And finally, if the Z2 action on the symplectic manifold is free, then you can just quotient out and get the same. This is like the Cartan isomorphism in equivariant in equivariant homology. I will also say something I forgot to mention, which is that by definition, if you look at the zero, so the ec, the zeroth term, the term that doesn't have an e in it, is going to coincide with the quantum differential. So it's going to be the usual d plus e terms, which account for the twisting and equivariant conditions. Okay. I'm going to make a small interlude of why one would do this in the first place and why it makes sense. And so I'm going to very briefly make a recall on usual Borel equivariant homology, cohomology. So if I have a topological space X with a Z2 action, the ordinary equivariant cohomology is the cohomology of the Borel quotient, which is just you take X, you take S infinity, and you quotient out by the diagonal action. This projects onto RP infinity and is actually a fiber bundle with fiber X, and the monodromy around the only non-trivial element in pi 1 is going to be the involution. So in some sense, what we're doing, so it makes sense because the non-trivial element of pi 1 is represented by going from a negative pole to a positive pole, and that's where we're twisting. So we're taking into account the monodromy in some sense. So this is where it all comes from. And we are basically considering a sort of fibered perturbation data. And for example, if you actually have no holomorphic disks or they all have too high Maslov indices, then you just recover the equivariant cohomology of your manifold. So it's the equivariant is a deformation of the quantum, but the whole thing is also a deformation of the usual equivariant cohomology. How do we compute it? So we start with L, that is S1 invariant. As I said, if it's S1 invariant, because of the Hamiltonianness of the action, it's going to be contained in some sphere. And then we have a projection from Cn plus 1 minus 0 to Cpn, and this defines a principal C star bundle. So C star or C cross is just complex numbers that are non-zero. Over Cpn, whose restriction to the unit circle defines an S1 bundle L over L bar. So I have the whole fibration, and if I look at the unit circle, it's going to be precisely the Lagrangian L. We're going to consider a special class of perturbation data called Biran-Khanevsky data. If I start with a regular perturbation data, when I say like usual, I mean for quantum cohomology downstairs, so the reduction is going to be monotone, and I can consider the quantum cohomology. And an S infinity family of data is going to be of Biran-Khanevsky type if the following are satisfied. The pseudogradients project onto the same pseudogradient, so the pseudogradient on the base is fixed. The projection to Cpn is pseudo-holomorphic, and the complex structure on the fiber agrees with the complex structure on C cross in some a bit vague term. And above each zero of the vector field downstairs, I have two zeros of the lift. I'm going to show a picture, but note two things. By the second condition, the equivariant chain complex of L is going to split as two copies of the chain complex because above each zero, I have two zeros. So I'm going to have one that's shifted by one because it's going to have a higher index because it lives in a higher dimensional space. And the other one is going to have the same index. Obviously tensored with K adjoint E. And note that our conditions imply that Pauli trajectories project to Pauli trajectories. And this is going to be really important. So here is a picture. I have Cpn, and I have the fiber C cross, and I have S1. And note above P, I have two critical points, X and Y. Above P prime, I have two critical points, X prime and Y prime. And and I can consider a gradient line is going to project to a gradient line downstairs. The pearl is going to project to a pearl downstairs, and the rest of the trajectory also projects. So this is just Biran-Khanevsky data. I'm picturing just for one from the non-equivariant version. But intuitively, when we consider the whole family, the S infinity family of Biran-Khanevsky data, what we're doing is we're keeping the base fixed. So what can happen? The involution is just going to twist the fibers. So I'm keeping CPN without changing anything, and I'm twisting the fibers as I go along from one pole to the other. This is sort of what we're doing. So it's a non-trivial task to show that you can find regular Biran-Khanevsky data. And with respect to the previous splitting, the equivariant differential is going to be of the form d e squared plus f, d and 0. So d is a usual quantum differential downstairs. E squared is just multiplication by the variable e, well, e squared. And f is a so-called Floer-Euler class defined by Biran-Khanevsky. And so, for example, I'm going to say a quick word on how you actually compute this. No, I'm not going to do the whole computation, but for example, what does the first d here correspond to? Well, it corresponds to counting equivariant pearls that start at x and end at another x prime. Okay, so because we choose Biran-Khanevsky data, in particular, we have this key property, which is there's a unique lifting of disks that is also non-trivial to show. And essentially, what we're saying is, okay, the pearls downstairs for the just for the regular quantum differential are going to lift two pearls upstairs, and there's a bijection between the two of them. So the non-equivariant part is just the same differential as downstairs. Now, for the higher E terms, you can rule most of them out by simply index reasons. For index reasons, since the projection is going to be a pearl, and because you sort of E is of degree 1, then if you have a term of e squared or e cubed or anything higher, then it's going to project to something minus 2-dimensional, which is empty by transversality reasons. And the only case you have to compute is what happens to the E term. And it turns out that the E term corresponds simply to computing continuation maps for the unit circle in just standard Morse theory. So this is just to give you a sort of idea of how you compute this. Is because you project and you geometrically see what's happening in the fibers. And after some homological algebra, you get so knowing the decomposition, you just compute what the cohomology is, and it's gonna be just the quantum cohomology downstairs, tensor k adjoint e modulo e squared plus f, and so we get a result. As you can check that this is isomorphic as a Z2 module to the direct sum. And if QH star of L bar is non-zero, then QH echo is going to be non-zero, and hence L is not equivariantly displaceable. This is where the key difference with Seidel-Smith's construction. Note that if regular quantum cohomology of L is 0, then by the Floer-Gisin sequence, F is going to be a unit. So in our case, since L is simply displaceable, not equivalently, but it's displaceable, then the quantum cohomology vanishes, so F is a unit. But then E squared plus F is going to be a unit in the power series ring, because it's going to start, because it starts with a unit. The 0 term is a unit. So this would be a unit, and if I'm quotienting out by a unit, I get 0. So if we had worked with a power series, we would have simply gotten that equivariant cohomology would also be 0. And there are generalizations. So if you have a Liouville manifold with a contact type boundary, such that the ref flow induces an S1 action, and you have an involution on the whole manifold that extends the Z2 action. So you have an S1 action, I have a Z2 action by just doing half the circle. And you also need a homotopy class condition for the lifting to work, but I forgot to mention it. Thank you.
Thank you very much, Julio. So I have many questions, but maybe other people want to ask first. Okay, then I start. Okay, so first I would like, can you go back to your first or second slide where the main result is?
Yes.
The very first. Oh, right. So I wonder about examples. So in the paper you have some examples. And so my first question is did you check whether it's a smooth or a symplectic result? I mean, one should check that you cannot do it equivariantly smoothly, right? That is really symplectic phenomenon. Is it clear?
Uh, in the case of we did check one case, which is I think if n equals 0, so if you work on C1, I think it's a topological phenomenon if you try to squish a circle without. But I
Well,
don't.
still
I actually,
you used area there in the proof, right?
yeah.
So if
maybe I can
So,
maybe I can add the comment. Well, Julio, maybe you go first.
well, I just wanted to say, because you also asked for some examples. So if you take any monotone Lagrangian in CPN that has non-vanishing quantum cohomology, then you just lift it to the sphere, and all of these spaces are not going to be equivalently displaceable.
right. So for instance, the Viana-Tori, but that's the second question. Did you check for the Viana-Tori in CP2 your cohomological assumption? Does it hold or not?
I don't know what torus that is.
You know, these exotic monotone tori in CP2. Now you lift them, or you can also start
yes.
in CP3, like Amanda Hirschi and other people did then many more. Now one should check the assumption, right? They have
I mean,
all
but
been
there are exotic tori in CPN that are monotone but have vanishing quantum cohomology, you know, so it depends. So the result doesn't apply to them, but I didn't
right.
check
Right.
if the same phenomenon happens.
So it's interesting to see when it holds and when not. Okay, very good.
Yes.
Mm-hmm. Mm-hmm.
I think Dylan wanted to say something.
Please.
Yeah. So one like if I slightly perturb the torus to be non-monotone, like I take a product of two disks with unequal factors, then it will be equivariantly displaceable.
I see.
Because
So
it's
you can
actually
even do it
displaceable in the reduction. So I feel if it's just volume preserving, it shouldn't be also true for the monotone torus that it's displaceable using volume preserving stuff. So I think it really is symplectic.
I see. You can even go away inside of Lagrangian equivariant isotopies. It's already not right. Mm-hmm. Good. Mm-hmm. So I will ask my second question, and then I shut up. So your examples all come from CPN, and then you lift. When you now take the Chekhanov torus in CP2, so you construct it in R4. So you cannot get him from CP1 because then you get the Clifford torus. So you take really the Chekhanov torus in R4 and put it into CP2. And let's take the Eliashberg-Bolterowicz construction, you know, a loop and then e to the I theta antidiagonal action. And then this is antipodally invariant. And I would like to know whether you can decide for such a very explicit and kind of important torus your conclusion. Because now you don't have the Biran-Khanevsky construction.
Because it's no longer going to be S1 invariant. No, but it's still the lift.
It is antipodal invariant, but it is not a lift from CP1.
Ah, yes. 。 Yes. But I wouldn't know how to conclude just based on the results so far.
Yes. Okay. I think this is a kind of a good example because after the Clifford torus, it's the next very explicit and good torus in a way.
Oh, I have a question. Isn't that torus just the not displaceable period?
Yeah, in C, when you lift it to C3, I mean, in CP2 it's not displaceable, but then you do your what do I say? No. What do I say? No. Sorry. My CPN blah blah was rubbish. I take it in C2 and I ask you a problem in R4. Of course, can I equivariantly displace it?
And it is antipodally invariant.
Yes, I checked. Yes.
You just check on our torus.
Yes. With the Eliashberg-Bolterovich construction, it is invariant.
I mean,
so for me, Eliashberg-Bolterovich is in like a T star S2.
No. I don't mean that one. So I mean you take a half plane in R2, you take any curve. Now you see the half plane sits in a plane and you U it as the total diagonal in C2. And then you write e to the I alpha gamma of t, comma e to the minus I alpha gamma of t. You sweep it by an antidiagonal S1 action. So this is the kind of the Eliashberg-Bolterovich construction of the Chekhanov torus in C2. And in this version, it is antipodally invariant.
Sounds a very good question. To be researched, I suppose.
Okay, good. So I should shut up. Who else wants to ask a question?
I have the following question. So assume it is displaceable. So you have some Lagrangian submanifold which is equivariantly displaceable. So can you say something intelligent about this equivariant displacement energy?
Yes.
From the, for instance, homology which you defined, maybe with some filtration and so on.
Yes. You can form you could a priori form with Novikov coefficients and everything. You could a priori form some sort of equivariant spectral invariance, and so that would measure the displaceability. We didn't go in that direction, but a priori you could. Then you should be able to, if you work over other coefficients, maybe you could read off explicitly what's the necessary Hofer energy to displace it.
Yeah, so then maybe you have the whole barcode and you have this boundary depth. Which
Yes.
Yeah. Sounds, I mean, maybe it's worth kind of pushing this. Thank you.
Great. So if somebody has another question he has forgotten, we have discussion time also after the second talk. Thank you very much again, Julio.